This was the endpoint from Tuesday, and this was the endpoint of the classical real-time programming environments like you've seen in Ada. We see a bunch of other languages today. Some much more frequently used, some much more rarely used. Any further questions about the state of the union in terms of real-time programming in imperative style, classical style? Not so far? Okay. Did you make sense of the labs? That worked? You ready to do some a bit more interesting things next week in the labs? Okay. So, brief word on languages which are managed, interpreted. Oh, that's a bit loud. To what degree you can actually make use of those in terms of real-time programming. Obviously, attempts have been made, and yes, there's something which is calling itself real-time Java. And what's the problems? What do you need to add to a classical managed language like Python, Java? What is missing there? Speak? Contracts. Could you add contracts?
Like repeatability in terms of like the government collecting etc. Always
Repeatability. We would like to make this whole thing a little bit more deterministic if you want to make that usable, of course. You want to have control over scheduling, control over dispatching, having the possibility of give me a process, give me a thread is neat, but a little bit more control would definitely be good. Obviously, if you work in a physical environment, you cannot abstract away from memory. You need to have actual physical memory access. And these languages are just built on the premise that you don't. And this is quite interesting. How do you write, say, a driver for a serial port interface in Python? How do you write a driver for a simple serial port interface or a USB interface in Java? Come on, you're all experienced Java programmers. How do you do that? You give up straight away. There must be some way to do this in C, yeah?
I was about to say the same thing. You write it in C and then you march it into Java.
Yeah, okay. That's a bit chickening out, so you just don't even try. Anybody would dare to try it?
Is there a library for that?
It is supposed to be impossible because memory is not a thing. Physical memory is not a thing in those kind of environments. But if you want to program an I/O device, just talking to a USB controller or to a serial interface, doesn't help you, right? You need to actually talk to a piece of hardware. So you need to have some form of memory access. You would need to form some form of synchronization. Do you have this in Java? Yeah, we have some form of synchronization. Is that sufficient for large-scale complicated systems? Of course, theoretically, yes. As any tiny piece of synchronization, if I give you an assembly level swap instruction or memory reservation instruction, is of course theoretically sufficient to design any kind of synchronization. Does that scale up if the only thing you have is synchronized methods and a synchronization instruction, a notification instruction? Because that's what you ultimately have. Right? And that's basically falling back from, on the one hand, you are feeling like you're working in a very high-level language. On the other hand, you then have to work on the level basically on semaphores in terms of synchronization. And handling asynchronous events, asynchronous transfer of control have to be added, timers have to be added to those environments, and they've done that. This leads to the actual specification of real-time Java, and I would say around 2005 or so, there was actually a massive interest in that. There were conferences and lots of workshops. How do you use real-time Java for industrial real-time embedded systems? And the community was actually quite listening up. It was a fresh kind of angle on the topic. We could leverage a mainstream programming language which has gazillions of libraries available, which we could possibly hope to use for hard real-time environments. So the motivation was clearly there, and the interest was also there. And unfortunately, this petered out pretty much. And I think for the last few years, this project could be safely declared as dead. Why? Can you imagine why this actually didn't take in industry? So it's definitely not for lack of trying. So they spent a lot of money and lots of workshops in trying.
Was it implemented?
Yes, it was implemented. You can download it. You can just run it. These real-time Java engines are actually available. You can download and run them. Yeah.
Also, there were like better options that they built from the ground up.
Of course. Anything which is built from the ground up is more structured and cleaner. Sure, but they said, let's try it. Let's see how far we get with that one. Where do you think they got too frustrated, or they just ultimately gave up with it?
And was it completely interpretable with Java?
Yes.
So you could have that, for example, and have guarantees.
You have backwards compatibility with this. It's the idea. I mean, if you don't have backwards compatibility, then you only combine the worst of all worlds. Then you don't have access to the libraries, and you have a wobbly interpreted language. So what's the point? So you need to have, of course, some compatibility with the rest of Java. But what do you get? More advanced threat models, particularly more advanced memory attributes. You want to have something like a real-time threat, a real-time process. How would you define, what do you have to do to a Java thread to make it real-time? A normal Java thread. Happily calling random libraries, memory is going in and out like crazy. Is that a real-time thread? How do you make this thing a real-time thread? The essential thing is you have to control its allocation behavior. If it just does allocation behavior like a standard Java thread, you have no hope, because then the garbage collector is actually required to keep this thing alive. The moment you have a garbage collector in the game, you need to make this garbage collector somewhat real-time compatible. And there is a lot of research about real-time garbage collection, which is an interesting field in itself. But the approach which has been taken was different. You have a number of different memory modules, and the real-time threads are no-heap threads. So you have Java threads where the moment you start a real-time thread, you have no longer the possibility to allocate anything additionally, anything new. It's frozen at this point. And while this sounds interesting, it is so much going against the whole Java programming philosophy that you will quickly feel that you're using a Java syntax to program terrible C sequences. You do everything which you have been trained to not do ever again in your life when you come from a Java world. You are forced to do just that because you cannot actually use objects anymore. If I cannot use objects anymore because I have a no-heap real-time thread, what's actually the point in the end? Okay. But I think it's a very honorable effort. If you look at that, what they have actually been doing there, they have been quite serious. And for academic reasons, I will actually come back to real-time Java every once in a while, because real-time Java, as being a much more younger approach to real-time definitions, like traditional real-time environments like VHDL or Ada or things like that, they actually defined a few things in a fresh and new way which we could possibly learn something from. Direct access to hardware timers is there, high-resolution time model. Yet the standard classes are still dependent on garbage collection, which is, of course, a big no-no in a real-time environment. And they kept it backwards compatible for obvious reasons. Okay. I think that's all what we need to say about, at the moment, about real-time Java. I'm not torturing you any further doing actually exercises in that kind of environment. If you feel so inclined, as I said, this stuff is available. You can do some real-time Java programming in your own time to see whether this makes any sense, or verify what I said about the awkwardness of having a no-heap thread model in a heavily memory-managed, classically memory-managed environment, and see how far you get with that one. Okay. Would you have wished that this would have kind of unified the world? Or do you think we should keep with more specialized environments? Okay, let's look at the world from a very different end. It's a bit from the French end. First, start categorizing systems which we have to build in three overall classes: transformational systems, interactive systems, and reactive systems. Transformational systems is the world in which you think and live if you do, for example, functional programming. Your job is you have some input data and you transform this into some output data. You're constantly thinking in terms of functional transformations in your system. If you think in terms of interactive systems, maybe you're more of a JavaScript guy. Everything what you're doing is based on callbacks and interaction with the user, and nothing has an easily transformational character. Everything is distributed, asynchronous, and responding to the user in a constant interaction and interactive environment. And the last one is a reflex-oriented system, a reactive system. A reactive system could be characterized by something which is simply defined by reacting to stimuli. Many real-time systems fall into that kind of characteristics. They're not hyperactive by themselves. They react to events. Something happens, you handle it, you produce a result. So it's all driven by a stream of input data, but not in a way like a user on a web interface, but a more cleanly defined stream of input data, as you will see how you can define this in a moment. Okay. The other characteristic should be a bit easier for you: data flow or control flow oriented programming. Do you know any data flow oriented programming language? What could that be? So?
Excel.
Why?
You have to Excel and you have to change down to Excel to the next one.
Yeah. How do you?
Express this program in the Excel.
Yeah. Okay. How would you formulate this as a data flow expression? Where is data flowing here?
One cell to the next.
Okay.
That's kind of the depends in your
Yeah.
equations or whatever.
Yeah.
Something like use of strings in Java, like the input strings, output strings.
No, that's actually quite different, because that's the streams in that context is basically a sequentialization operation, marshalling operation.
Is Haskell a perfect example, or am I thinking some different subtopic?
No, Haskell is a classical example for a transformational language. Data flow, Haskell would be, I think, a data flow language if it would have a stronger concept of concurrency. So if you could express Haskell is in, there are lots of things which can happen. If this happens, I do this kind of transformation. If this happens, I do this transformation. If both of them happen, I do both of these transformations. If I could program in Haskell like that, yes, I could interpret this as a data flow language. That's a good point. But it requires that you have not just one single data flow, but you model your whole thing as a set of data flows.
And with something like artificial based something that
OCaml, similar argument. OCaml is actually closer because you have more concurrency in OCaml than you would have in Haskell. So yes, it's closer to that one. But actually, I heard mentioning of another language in the last lectures, which is actually closer to data flow modeling. VHDL could be much more considered as a data flow language because here you're designing electronic circuits ultimately. And if you have a free form of designing electronic circuits, that can be easily used to define data flows. It doesn't mean that VHDL is always a data flow language. It's not at all. But you can much easier use something like that to program that because you have close to unlimited concurrency in VHDL. You don't quite know what I'm talking about. We will talk about VHDL in a moment in more detail to see that, yeah.
Why have we not brought up Ada?
Why are we not what?
Not brought up Ada. Why does Ada not qualify for this?
Why does Ada not qualify as a data flow language? Ada is a more classical control language because the concurrency is there, but not in terms of I can formulate 100 data flows completely independent of each other. It still has the concept of you define a process, the process synchronizes with something, and then these processes exchange messages. It's not that you can formulate data flow A completely independent of data flow B without needing to tell Ada instantiate this, instantiate that, synchronize with these kind of things. So if you put it like that, then pretty much every serious concurrent programming language would qualify for data flow. Yeah? But I would say actual data flow language focuses on this aspect and has a much lower emphasis on control structures. And Ada is simply still a very classical control structure heavy language. Yeah? Okay. Erlang is a good example. Anybody familiar with Erlang besides you? Erlang is one of the other classical concurrent programming languages. It's the tossed up candidate whether you do your concurrent programming course in Ada or you do it in Erlang. Erlang is the functional programming version for that one, very heavily based on message passing. Unfortunately, Erlang is pretty weak T on the type side, and so I'm not tending to overuse it. It's a bit aging in that sense. But yes, Erlang is probably qualifying quite nicely. Pretty highly concurrent. And Erlang has the advantage that somewhere between, say, Ada and Chapel, you can very quickly define 100 concurrent operations in Erlang very, very quickly. Certainly quicker than in Ada, not quite as easy as in Chapel. So it's somewhere in between. You had another comment? Yeah.
I just about to ask, is Chapel kind of data flow?
Is Chapel a data flow language? I wouldn't say so. It's still no, not really.
Kind of compared with Ada, you have less control over how concurrency.
Yes, but it's not independent data streams. It's still, you have one vector which is spreading out into 1,000 different concurrent operations, but you don't have a number of independent data pipelines which you model side by side in the same language. Right? Okay. While in VHDL, for example, you can just reserve some area of your chip for this data processing, and you have another area for your chip for a different set of data processing. Before you know it, you have 10 parallel data streams which have very little to do with each other, which possibly synchronize a little bit at some point, but they could be clocked differently. They could be unclocked, some of them. They could be completely are combinatorial. And that choice and that power of having this all concurrently and independent of each other, this is hard to come by in most other programming languages. Okay. So SRL, there are similar languages to SRL. Other languages are called Signal. Signal is the data flow companion, so to speak, to SRL. SRL focuses on the control-dominated side. SRL is designed to be used in control-dominated reactive systems. Are there any of those? Plenty. A lot of real-time systems are qualifying for that. So SRL is not defined for the heavy data flow, but is defined for the precise, responsive, reactive system design. Process control, control logic hardware, you can, again, similar to VHDL, so if you take the control part of VHDL, you can design all of that in SRL and then translate it to VHDL if you like to. The advantage of that one is SRL is, from a logic side, much easier to prove. So this is a little bit easier to be made compatible with a theory improver than what you would be able to do in VHDL. Defining communication protocols is a classical one. We all think that defining communication protocols is a bit of bit banging and following a protocol, but those are classical areas where small mistakes lead to catastrophic failures because your protocol goes out of sync. You lose communication with the other side. You cannot recover from it. You don't have the right protocol implemented. Verifying your protocol is a classical area of program verification. And so that you can actually verify your protocol, you have to formulate it in a way that it's close enough to a logic expression, and SRL helps you with that. So I think we should look at what that means in terms of programming. So if you program in SRL, that's the overarching assumption. The overarching assumption is this is not data flow transformational, this is reactive, and we assume that everything is instantaneous, what you do in SRL. Nothing takes any time. Strange idea for a real-time programming language, that you just bluntly ignore time. As a matter of fact, this is nothing but committing to the truth that if you work in a theory improver environment, you have to abandon time at some point or discretize, at least make time discrete to a very high degree so that you can actually work in these logic environments. And this is just making the ultimate point of it. I'm saying if I want to prove these transformations, I assume that the transformations themselves are all zero time. This is what your theory improver will see. In terms of your physical interaction with the world, what that means is that there is no observable delay between stimuli and reaction. So your system is getting triggered, and in the context of your application, in the context of your system at hand, you cannot measure, you cannot observe that the response of the system is sometimes a bit faster and sometimes a bit slower. You cannot observe or measure that. I'm trying to formulate that very carefully. This is from the perspective of how fast your system has to work, how fast your system has to be observed. It is usually the case that we are still producing a physical system here, which has some silicon in the game, and it is not hard to define an observer, just have an additional observer, which will tell you that there was a delay in your response. But maybe the next one is actually more interesting. Think in terms of the sampling of your system. How often does it make sense to look at your system, to check the state of your system? And this is dependent on, for example, the mechanical inertia of your system. If you have a car going at a high speed, what kind of sampling frequency makes any physical sense to measure the speed of this car. You measure the speed of your car. Is your speedo actually clocking the RPMs on your engine on a gigahertz basis?
Would it be relative to the observable rate that the information is required? So for your speedo, it wouldn't be like human recognition.
That's one aspect of it. But the other aspect is also how fast can your engine actually change speed? How fast can your car actually change speed? Usually, of course, that's a big problem, because if cars could change speed faster, we would have much less accidents. But cars cannot change speed that fast. If they're going at a slower straight than 110 kilometers per hour, they still take 50 meters before they get to a still stand. Right?
Something to do with frequency.
Yes, that's of course related to that. That you assume what is the highest frequency which can possibly ever occur in my system. And if I want to express this in terms of Nyquist, what is the highest frequency my signal can ever change? And I look is, what is the change rate of my speed? How fast can I accelerate and decelerate my car? This is probably not gigahertz. This is probably not megahertz. This is, if you're really lucky, maybe in some 10 milliseconds range, maybe 100 milliseconds range, where you have any reasonable response to that. Right. And in that context, now we define an observer in respect to that system, as it's no point observing the speed of your engine beyond a certain speed. And now, translating this back into that kind of programming model, if my engine controller can produce a new motor signal in a time which is shorter than that, it is, from a logical perspective, considered instantaneous, because it doesn't make any difference whether I produce this signal in 1 nanosecond or 2 nanoseconds. Is absolutely irrelevant with respect to the observability of my system. Right? You're many orders of magnitude away from what you can observe from your system. Then you can logically consider this instantaneous. That's the approach here. And now that we got this off the chest, then you can go into, I ignore the time, as long as I can make sure this is the case. So you need just some overarching sanity checker. Do you have any infinite loops in my system? Do I have any recursions, infinite recursions in my system? Of course, that's big issues. If I don't, I can roughly estimate how long that takes, and I can say this is still an order or 2 or 3 orders of magnitude faster than the overall observability of my system. Instantaneous, I don't care. Right? That makes your world easy, right? Of course, only works for systems where the CPU power is so high with respect to the overall speed of your system that you can afford something like that. But often you can. Does that make sense? Cool. Excellent.
What real-time systems would that fail? Where would you have memories of CPU power?
What real-time systems would that fail? Yeah, it's actually a good question. It usually fails. You find out if your CPU, overall CPU load in your system is, say, reaching 20% or exceeding 10% of your overall CPU. You know that you actually do quite a lot of number crunching with respect to the external observation, and you're already getting pretty close. These systems are classical systems where the CPU is most of the time asleep. So you wake it up based on external stimuli, do something very quickly, and put it to sleep again, because you have another tremendously long 100 millisecond delay before anything else will happen again. So you actually you power your whole system down for the next 100 milliseconds. There's nothing happening there anyway. And that means the overall CPU utilization which you have is less than 1%. And I said, if the other case is true, that you have a CPU utilization which is beyond 20-30%, then it's usually that you have to start thinking about a way, thinking different from a responsive reactive system. You have too much number crunching in there, the processing is too high. Classical data flow oriented applications are not lending themselves to that. If you have, for example, classical real-time application, you have one of these big audio consoles on a big concert. These audio consoles for the last 15 years are all digital. So the times of mixing that analog is long history. But what does that mean? They're all digital, which means they have actually CPUs in them. And they're actually processing, sampling, filtering, doing this all with algorithms or with specialized CPUs to do this in there. And these CPUs are going pretty much full blast. There is not much wiggle room in there because you have usually some at least 24-bit resolution inside these mixers. And this is a significant amount of data. Plus, you over the last few years, you also mix your video streams usually in the same go as well. So on top of that, you have also a video signal to process. And latest at this point, when you start processing your video signal through the same console, then your CPUs are usually flawed pretty harshly. That's the opposite end of that. And here, a tiny variation in your algorithm will lead to very different responses. And you will immediately notice a catastrophic change in the output. And if you hear that your audio signal in a large concert starts clipping, it's not only unpleasant for the audience, they're actually exploding amplifiers all around you. And maybe, I hope you have never seen that, but you have usually these amplifiers just behind the stage somewhere. And you do see them exploding if they go bad. And at those power ranges, there is no protection against that kind of clipping and overload. They're just burning down. And that's not nice if you have a big international band on stage and your mixer has just been messing up because the famous programmer from the ANU actually messed up in that process, right? So that's probably a good example for a data flow-oriented environment. So how does a SRL program actually look like? If you have these kind of environments, you're often thinking in terms of state machines, state transitions. This here is an example for a Mealy machine. You all remember those from your childhood, from your early days at the ANU? Like not? Okay. You know what a Moore machine is? Yeah.
One of the two is a state machine where the next state only relies on the input, and then one relies on the input and the previous state, if I'm not mistaken.
No, it's even simpler. The Mealy machines are producing the output in transitions, so you're producing events, while a Moore machine has a permanent output during a state. So the output in a Moore machine, maybe this is actually what you said. It's close enough. So close enough. So in a okay. So in a Moore machine, you would just wire the output to each individual state. If this state is there, you have a certain output. In a Mealy machine, you're not thinking in terms of persistent states, this is on or off. You're thinking in terms of events. And every time you have a transition between one state and the other, you have the possibility to emit a number of events into your system. And these new events can then trigger new state changes. That's the philosophy of not the philosophy, that's the definition of a Moore machine. Mealy machine. Now I'm getting it confused. Okay. But I mean, state machines is something you have seen before, right? Good, I'm relieved. That was a bit of a shock. Okay. So now you can draw colorful diagrams like that, or you can write down a simple SRL program. And most of the simple SRL program is just declarations. There's barely anything there. You need to have event A and event B Once you have both of them, you emit an output. Not a tremendously complicated state machine, but you need to actually write that down. So you have to unroll that. What happens if only event A happens? What happens if only event B happens? So you need to store that. So you go to a different state. You go to event A, which means that you transition from here to there. So you have event A but not B yet. You have only B but not A. You have A and B. You immediately emit your output. You're in this state, which means you have received event A in the past sometime. Now you receive event B and you emit your output. And symmetrically here, and you have the possibility to send a reset event to your machine to undo everything. Formulated very simply in, we have input events ABC, output event O, and now we do, that's an interesting construction here, loop with every R. That means we are restarting our loop on event R. Otherwise, these two statements here are sequential. Statement 1, statement 2. Statement 1 is a concurrent operation, which means that concurrently we're waiting for A as well as we're waiting for B. So we are emitting two processes. One is waiting for A, one is waiting for B. Once both of these processes are completed, the concurrent statement is completed. I can go to the next state, which means I omit the output. Simple enough? Cool. Let's do something more fun. Let's program speedometer for your car. I could program that defining those things. I have inputs, which is one event for every meter your tire passes on the road. Every meter, I want to have one signal from my car. Easy to implement. Right? Then I have one other signal, which is triggered every second. And you see that at this point, you have a stream of events which gives you the meters passed, and you have a stream of events which gives you the time passed in seconds. Obviously, you should now be able to calculate the speed of your thingy. Right? How do you do that? Well, you have to accumulate how much distance you already passed. So you have a local variable distance, which you initialize to 0. Then you do the following. You accumulate here all the meter events. For every meter event, I'm incrementing my distance by 1 meter. And I abort this, I stop this, when my second event comes in. My second event comes in, then the distance which I traveled so far is directly proportional to the speed. Because in this case, this is distance per second, or the distance which actually your vehicle traveled over the last second. The most precise speed measurement I can do. No smoothing, no averaging here. It's just the speed which actually happened over the last second in the granularity of my event stream. That's all nice. And there's an interesting one here. I have a declaration which defines the relation between meter and second. And this is necessary because I define the relation between meter and second here as mutually exclusive. I define as these two events cannot happen both at the same time. If they happen both at the same time, my system here is quite wobbly. So what does that mean? If they happen both at the same time, did I actually count the last meter? Or did I abort this first? Well, this is a non-deterministic, pretty wobbly situation, hence I forbid that. But in practice, I probably need to respond to that because this is SRL. So we have a very a rather slow granularity of the thing, and the possibilities that meter and event is actually a second and meter is happening at the same time is rather high. So I need to actually handle this at some point. In order to do that, I need more precise synchronization formulations in such a reactive language. We have those first 4 synchronization points, which are the basic ones: wait for a signal, abort something when a signal happens, repeat something every signal, or repeat this loop as a whole with each signal which is coming in. And I can add something. The first thing which I can add is I can add an immediate to these environments. An immediate means that this is hardwired. This will always happen. I cannot abort this. I cannot stop this. This is always happening first. When these signals happening, I will immediately execute this thing before anything else is happening with my system. And so this is just simply doing that. And that means I have now implemented something like a level trigger. I don't care when this exactly changed. If this has changed at all, I will take this into consideration, not in relation to anything else. And the counter possibility, the flip side of that one is that I have weak abort, which means that all of these abort operations could be attributed as weak aborts, so that if it actually happens, I still have one last wish, one last round of my operations before I actually abort it. So instead of instantaneous abort, which is the default operation, I have a weak abort. If this happens, give it one last chance and then abort it afterwards. If I have that, then I can formulate that in a number of different ways. This, what you see here on the screen, is wrong, because now I removed the mutual exclusion thingy, and I don't know when this exactly happens, but I have to simply attribute my abort statement with a weak abort, and I know that even if they happen simultaneously, what happens inside my abort block will always be at least executed one last time, and I'm good. And I know that if they happen at the same time, I will count the last meter, and then I will abort the whole thing. Alternatively, I don't say it's a weak abort, I say it's an immediate response, which means that with every immediate signal on the meter side, I will always hardwire the response on the output side. So these responsive systems, you have a bunch of events happening and you respond to them, need to be carefully considered in what sequence this is actually happening. If there are conflicts in terms of if multiple signals will try to rip your signals in different directions, you have to be careful that you're not introducing non-determinism in that process. This is the flip side of what you have to pay for losing the sequentiality of your system. That is a responsive, reactive system which is only triggered by events. Yeah.
With the weak, how is it now non-deterministic? Because if it's waiting for one more, is the one more non-deterministic, or is it that one plus the next one?
No, it's just simply dividing the responses of my system into different phases. You see that you will also have this later in the VHDL examples, that sometimes you need to shift the responses from your system just by a few nanoseconds to make it deterministic. If it actually happens at the same time, then you're in trouble. If you just shift the response by a few nanoseconds, you're deterministic again. Hence you see so often little nanosecond delays in your hardware description programs. And this is the logic equivalent to that, so to speak, that you just take this off the current hard edge of my clock signal just a little bit so that they don't actually being evaluated. You know they're not evaluated at the same time. So it's a trick through the backdoor to introduce some level of sequentiality again to your programs. That's the idea. Okay. So, and another aspect which comes in these kind of systems, causality is problematic. What does causality means? Basically, you need to make sure that you don't have any forward references in your system. And in a more technical environment, that means two things. It's reactive. They have a well-defined output. And it's deterministic, that you only have one well-defined output for the whole thing. Okay. Let's program purposefully against that. What's the easiest possibility to produce a non-reactive system? If my output is present, I produce the output. It's basically a dead wire. This is not responding to anything. A non-deterministic output. If my output is currently present, then I emit my output. As opposed to the first one where the output is currently present. If it's not present, then I will set it. So it will always have an output. So this will just simply be an on-wire implementation. This thing here is not deterministic. If I have a 1 on my output signal, I send a 1 to my output signal. How is this non-deterministic? Doesn't it sound pretty deterministic?
Depends how you initialize it.
Yeah, I don't initialize it. That's the non-deterministic part. I don't know what the state of my system is when I start this calculation, which means that it simply depends on how it randomly falls during startup into my output event is there or not. If it's there, then I just repeat it. Otherwise, I don't. And the more classical and more practical example is the last one, that you have simply cyclic dependencies. That means if A is currently present, then emit B as the next event, and A is going away. If you have B present, then emit A. And you have now flip-flop relation between these two events, and they're cyclic dependent. Yeah?
In one of those you have then, but in the other you have else.
Yeah. If B is present, is not present, then emit A. It doesn't actually matter. Both cases are cyclic dependent. So I can also write it then here, still cyclic dependent. Right. Point is not what kind of dependency you have, but that you have A is dependent on B and B is dependent on A. Right. Okay. So now the big question is, you want to write your theory improver. You want to verify your system. What would be the first suggestion you're telling these programming language guys? Oh, you will tell them cyclic dependencies are rubbish. As the moment you have cyclic dependencies in my system, this is opening the possibility of any kind of non-determinism, deadlock, non-causality, in other words, in my system. And I can just wipe this away by saying my system is supposed to be well initialized and cyclic dependencies syntactically forbidden. I cannot have cyclic dependencies. And there are programming languages which do just that. This is super strict. But what's the price to pay if you forbid cyclic dependencies? Well, it's hard to know, and I can tell you. If you forbid cyclic dependencies, you simply have to unroll all possibilities manually by lots of new events. And that makes your program simply larger, potentially a lot larger, if you have to unroll that. The possibility of formulating this with cyclic dependencies gives you much more elegant expression possibilities. This is like saying my programming language has the potential of doing deadlocks. I can, of course, restrict my programming language to not be able to do that, but then my communication, my message passing possibilities will be severely limited in my system. Talk about a few other possibilities later on in the course as well, by the way. If you want to make sure that your program terminates, what kind of programming language do you design? Can you design a programming language where the halting problem is solved?
Yes, but it's not Turing complete.
Yes, but it's not Turing complete. What would you do to your programming language?
All the programs terminate when it started.
I was thinking about something a bit more subtle. Yes. You remove while loops and recursion. This is exactly the point. And there are programming languages which do exactly that. No while loops, no infinite recursions. You can actually, in some of these languages, do have recursion. Like you can have a for loop. So the bound recursion equivalent, which equates to some for loop expression, that's all right. But you have to syntactically make sure that it's not infinite recursion. You can make sure that it's the case.
Is that Turing complete?
Is that Turing complete?
Yes.
What do you think? Not Turing complete?
Turing machine can do many things, right? And surely that's not able to do many things. Then Turing complete.
So it's not Turing complete. So, if you want to define, this is a classical discussion in the community which, for example, designs communication protocols. If you want to design your communication protocol, I can give you a Turing complete programming language to do that. Define your new USB protocol, your real-time programming protocol with a Turing complete language. Well, you have tons of possibilities to shoot yourself in the foot in the process. Can you define a communication protocol with a non-Turing complete language? In almost all cases, you can. It's usually a little bit longer, but you have the blind guarantee that this thing will terminate. And that can, in many situations, be the striking advantage which you actually want. You don't have to waste weeks of analysis in trying to prove termination of this program, because this program terminates by design, all of them. Right? So the loss of Turing completeness is actually, in practice, often taken into consideration. Okay. Funnily, not in SRL. SRL is not that brave. SRL allows you to have cyclic dependencies. How would you implement a compiler or runtime for something like that? Quite simple. You have a system which collects all current input signals and calculates immediately all the responses. You have a combination logic doing that all for you. You emit your output signal, and then you wait for the big synchronization signal. So your whole system is dependent on one central clock, which is, of course, very slow in comparison to what you are used to in terms of clock. So this is not gigahertz. This is probably in terms of 10 milliseconds, something like that, maybe 1 millisecond. It's very, very long for anything you do on your computer. And as long as I can guarantee that my programs somewhat terminate, don't have infinite loops in them, this is usually not very hard to get in, to keep in those kind of bounds. Okay, but that leads very quickly to a concept of logical time or discrete time in my system. You wipe away real-time continuous time to some degree, at least. We will come back to that one again when we talk about your interpretation of time. What do you think time is and how we have to define time? We have to be a bit more precise in that. So does that make some semi-sense so far for you? Just need to show you the field here, that it's not all just plain C programming and how to interface with a controller. The design of these real-time systems have to happen on very different levels. This is on a quite high logical level to do that. Okay. So another interesting candidate to discuss, VHDL. Some of you have had exposure to that. Some of you have had exposure to the weak T alternative to that called Verilog. As an output, they both do the same thing. They can be used to program, for example, FPGAs. Difference in VHDL is a completely strongly typed environment, as opposed to Verilog, which it's actually quite cartoonish, I have to say. Verilog is basically appealing to the C programmers. This is the whole syntax of Verilog is very C oriented, and so is the type system of this whole thing. So you're in control, man, do what you want. That's the kind of Verilog philosophy, and this appeals to the ADA programmers here. VHDL is the naggy one, which has tons of error messages and checks and type conformity and gives you all of these kind of possibilities. And I have no idea why people designing hardware would not want these error messages. Because an error message of this is actually not type conformant, producing a piece of silicon, not a piece of silicon, a piece of FPGA code, which is actually running in hardware later on and just simply blowing up on your FPGA side. Why wouldn't I want to have an error message telling me so beforehand? But you're in control, do what you want, your compiler will do exactly what you want. So that's the Verilog philosophy of this whole thing. What can you do? You can interpret this as a data flow oriented language or control flow. That's usually the time when this whole thing powers down. It seems to be somewhat automatic. I would assume that is also connected to echo. Has anybody tested the echo recordings for this whole thing?
Yes, it doesn't capture your slides. So you capture the first slide and your audio. That's it.
It doesn't capture the slides.
No. It only gets the first one, and then stays with the whole time. So you're watching like that. This is one very dead slide.
Obviously, your 360 will be fully verified.
No, it wasn't at all verified.
Okay. Hey, hello. Just switch it on. Projector is not warming up. It's a laser projector. Okay. Anyway, we'll come back. A side remark, if you have any issues with Echo 360, maybe not in this course, but in any other course, please immediately dump a response on help desk. Please do that.
They really hate most of us.
Good. No, it's not good. But the response is usually that, Echo 360 is perfect. We have only a handful of comments during the semester.
Does the same with Waddle? Because I told them about the prepared execution on it 4 months ago and they still haven't fixed that. And when I say told them about it, I posted on the public forum within Waddle.
Oh boy.
Well, my Waddle requests are about 4 years old. I don't think they're responding very swiftly. Diplomatic trying to. But it's your services. And you are the customers of Echo 360, Waddle, etc. And just if your stuff is not working, you are literally paying for this. This is where part of your money is going here. And if this service is constantly broken, you have to respond to that and just kick them to get this under control. Echo 360 is on the blink for the last week. The whole last week, most of the audio recordings were gone. So now we have the opposite. Some of the audio recordings are going and the video is not coming. So they're trying to get this under control, I assume. So VHDL, back to the fun parts. Programming with packages and generics. Guess where this is coming from. You do have actually entries in that whole thing. You have all data types available, including the enumeration types. And this is important. You can either not clock your stuff, but you can also clock your individual modules completely independently, which is something you're not familiar with. That's not syncing in with somebody coming from sequential or concurrent programming at all. You can clock your devices completely independently. You have to make a choice of that, what kind of clock you want to use there. Why don't you just use the same clock for everything? Come on, CPUs are doing that quite successfully for a while. You don't have different parts of your CPU clocked differently. Well, actually you do, but but not to the level of which you are actually modeling a CPU at the moment in terms of the state transitions. Why does it make sense to have completely differently clocked modules in your system?
You have two devices with different clock rates.
For example, yeah, simply. If you want to respond to an input channel, most of your input channels in your real-time devices, they're coming with a certain frequency, which means they're defining a certain responsiveness, a certain clock for you. And so you define the clock which matches somewhat the data flow which comes in on that channel. So the clock which, for example, measures the speed of your car will probably be a different clock than the clock which processes the video images which you take with your car, quite obviously. Concurrency is beyond supercomputer level, so I have potentially the option of offering a little baby cray to the concurrent systems course this semester, which is just a little 2,000 node machine. But 2,000 nodes is not much in comparison to what you do on a VHDL machine, where you could have anything concurrent as much as you want. Right? I mean, this is not 2,000 CPU cores, which you can do on an FPGA environment, but 2,000 much simpler operations. If you want to, for example, produce something which works on a video image as a whole, one of the first thoughts for a VHDL programmer is, can I make this small enough that I have little processing units which are hardwired or which are triggered by every little pixel which I can serialize into my system. So you serialize your whole picture into your FPGA chip, and then you do the same filter operation, the same mask, whatever you want to do, on all of your pixels absolutely simultaneously, if your FPGA is large enough to do that. That kind of thought is not something you have in classical programming languages, because that's even beyond supercomputer level to have those kind of number of gates available. Yes, and protected types still exist. Trying to formulate the same thing in VHDL, so our state machine. If you want to formulate a state machine, transforming state machines into electronics, into logic. What's the concept? How do you do that? What's the equivalent of electronics components to a state machine? Besides that is on the screen. You know what a flip-flop is, right? That's just storing a state and transitioning to a new state with every clock cycle. I think that's a very useful component if you want to define a state machine, because that's the central element where the state of your machine changes from one state to the new one with every clock cycle. The rest of your state machine is all the combinational logic, which looks at all of your input and produces all possible following states. And that is combination logic, which is completely unclocked. You can imagine this as a bunch of logic gates. This is the rest of your state machine. Right? So how do we express that? We define our states. Start A detected, B detected, or AB detected. And we have now different attributes. The enumeration and coding of our states can be of the type one hot. One hot means that you're encoding the state with always only one active bit in a word or in a bit vector. It's not necessarily a word, right? Because the number of bits is completely variable here. But you have an array of bits, to put it logically, and only one is active at any given time. This is the one hot encoding. You can also encode this in gray. That means what? Anybody heard of gray codes? Yeah. Yeah, go.
There are two sequential states, one have one bit of difference.
Yeah. That means if you move through your state space sequentially, from one state to the next one, there's maximally one bit flipping about. Now, one hot does not satisfy this. If you have one hot, that means from one state to the next one goes down, the other one comes up. That's 2-bit change. Can you imagine why we have 1-bit changing state encodings?
Minimization, so K-maps, you can use it to minimize.
Minimizing what?
The expressions, the Boolean expressions.
Not really.
So it's like you don't have an intermediate value which is incorrect. Like, so if you're changing between two states, you only have to change by a bit, whereas if you change between multiple bits to change, you can potentially read a state which is wrong.
It's an observability problem. If you look at your system, this is a system which does not necessarily have a clock. So it's combinational logic. You look at your system and you want to make sure if this bit is this one and this bit is this one, you do that. Now, if they're only changing one at a time, this is deterministic. If they're changing both at the same time, this is problematic. Because, as you said, there could be inconsistent states where one bit is flipped, the other one is not. The other one is flipped, the first one is not. Both are flipping at the same time. They're all different intermediate states. And that introduces new states in a system which you possibly don't want. Unfortunately, gray codes, sorry.
No, just after you finish, it's just a question. I'm trying to wrap my head around what one hot is. So do you have a single bit assigned for that state, and where that state, that bit's flipped?
That means simply if you have bit 0 is state 1. Bit 1 is the next state.
Oh, okay.
So each bit is just representing as this single bit this one state, which means there could never ever be a situation where where 2 bits are active at the same time. That would be inconsistent.
And we would represent transitions in a different way, or is that?
That assumes that my transitions are messy. So I have to make sure that my transitions have enough time to actually transition from one state to another one, so that again you don't observe these intermediate states where one bit is almost already switched off, but the other one is not on yet, which would be again a non-state. Right. Other possibilities, well, you encode it in binary. Why would you do that?
You need fewer bits for the state. However, you have to compare them to realize what state you're in. Compare all the bits, whereas one hot don't have to compare one bit.
Yeah. So if you have 2,000 states, you begin slowly to imagine that 2,000-bit vector is a bit clumsy. Or you're simply a computer scientist and you think binary is the best thing since sliced bread. Everything has to be binary encoded because that's how the world goes, right? That's actually a quite rare choice on VHDL. Because can you imagine what another upside of one hot encoding is? As opposed to binary, you actually almost hinted to the upside of one hot already.
The speed to check a state.
if you want to make something dependent on a specific state, in terms of electronics, in terms of logic, what do? You just wire to that bit. Job done, right? You don't need to have a decoder in between. So that simplifies the whole logic quite significantly if you have a one-hot encoding.
Wait, so
Yeah.
sorry, VHDL is almost always one bit per state, not one. Is that the takeaway?
That's not VHDL. That's quite common. It's just the common encoding is usually one hot. Most programmers will use one hot as a default, as it simplifies logic. I wouldn't say this is VHDL specific. VHDL gives you many other possibilities as well. You can also control the Hamming distance of your encoding. Why would you do that? You know it. It's just. Why would you increase the Hamming distance in your system?
So can we just get clarification what the Hamming distance is?
Yes. Anybody wants to explain what the Hamming distance is? Yeah.
So that's the number of bits that are different between the two.
Yeah. So it tells you the encoding distance between two valid states. You have one state which is defined here. You have another state which is defined here. How many bits do I need to change to get from one to the other? That's in rough terms. I mean, the Hamming distance is mathematically defined a little nicer, so I'm simplifying here a little bit. But roughly speaking is how much change do you need from one state to the other. Why would you want to control that? Why would you want to say, I want to have a Hamming distance of 10 bits? Yeah. The moment you want to send something in an airplane, classically you actually increase your Hamming distance because you have constant cosmic background radiation. And it simply happens occasionally that part of your memory goes wow, and some of your bits are getting a little bit in the wobbly state. And if you have a large enough Hamming distance, what can you do?
Recover the original data.
Yeah. You can detect it fairly easily because the statistical chance that you will coincidentally, due to cosmic radiation, fall into another consistent state becomes smaller and smaller with larger Hamming distances. So first of all, you're not accidentally falling into the state landing gear out just by cosmic radiation, right? Yeah.
Would we also need to do error correction with a large enough?
Exactly, is what has already been mentioned. If the Hamming distance is large enough, then you can also measure, am I closer to this state or closer to this state, depending how many bits have been changing there. And then you can also do some error correction attempt by saying, likely I only had one or two bits actually flipping, which means the next consistent state is this one. I can correct that. Yeah. No, you have to do this manually. It's not quite that comfortable, but it's also not that. You can also just use standard. This is, in VHDL terms, this is a piece of a standard library thing. It's not part of the language, but you can just use common coding to do that. But obviously, this is something other people thought about before to do that. Okay. We're not quite done with the VHDL code. So we only defined our state. Then we define signals. Current state and next state, both of the type states, and I define two processes. Now be careful. Processes means something very different in VHDL than what it would mean for you as a computer science person. Process is just a bunch of logic, to put it bluntly. It's not related to anything going through a scheduler or something like that. So the first process is what I call the synchronous process. It's dependent on the clock and reset. You also see that the clock in itself is not necessarily anything special. It's not that you have a clock which is defined as something different. It's just another signal. And my clock signal is having an influence on this process. And the process is defined as the first thing is if I have a reset signal, then I set the current state back to start. Okay, so far so easy. If I have a clock event and my clock is now 1, clock event means it changed. And it changed, and afterwards, when I now look at it, my clock signal is high. That means I must have changed from 0 to 1. This is what I want. So with every transition from 0 to 1, as I also indicate in this flip-flop diagram up there, is positive edge clocked. I want to assign the next state to the current state after 1 nanosecond. Right. That's a reflex which the VHDL programmer puts into the whole thing. After 1 nanosecond, come on, this is a bit nitpicking. Why not 1.5 nanoseconds? Just to make clear that you explicitly, yeah?
The whole delay, just to make sure that everything has settled down before you assign the...
So you want to calculate this, and before you actually assign it to your output, you make sure that nothing changes anymore. To suppress any potential race conditions in your computational logic, that you have a clean signal on the other side. Which reads completely weird when you look at it from a sequential programming perspective. Yeah?
Is this greater than, or the less than you can assign? Is that different in Verilog, where it means it's non-blocking? So it assigns, does the assigning after the condition is over? Or is it just assigns it exactly?
No, this actually assigns it directly.
Okay.
Yeah.
Isn't that horrendous practice?
Horrendous practice?
Yeah, the after 1 nanosecond check.
What, that you have to say this manually?
The fact you have to describe it that way. The fact that there's okay, it could go wrong, but if it goes wrong, then it'll probably go wrong for a very short amount of time. So we'll chuck in an arbitrary number and out of there.
Yeah, and no, it reads weird when you see this for the first time. Once you're actually getting a bit more used to thinking in terms of electronics, you don't think much about these things. Adding a 1 nanosecond delay basically means what you're trying to formulate, I think. This is just, I make sure by putting an additional nanosecond in there that all my potential races with a handful of AND gates have been all settled down and it's all calm. And you begin to think in those kind of terms very quickly. So for VHDL programming perspective, that doesn't look weird. It looks perfectly normal.
And if I start doing this in Ada? Okay, maybe not.
Yeah, if you get your Ada runtime environment to actually respond in nanoseconds, that would be quite nice. Here you have to guarantee that these nanoseconds are actually pretty close to what will actually be introduced as a delay here. Probably not exactly nanosecond, but close enough. In your runtime environment, on your Ada environment, you think in microseconds, not in nanoseconds. So, and I have a second process, which I call the combinational process. The combinatorial process is dependent on the current state and the events, the signals A and B. And this is a big case statement. How do you read this big case statement here? What is produced on the other end? You have your VHDL compiler. What does this produce?
Is it a multiplexer? So it checks what current bit is then outputs the correct.
Somewhat, or even simpler actually. What does this compiler produce technically?
It depends on the synthesis of the compiler, but usually this will be a piece of ROM that just has an input and gets a single output, depending on the input combination.
Yes. In logical terms, if you want to write this down in as...
It's just a functional AND gate, right?
It's a what?
Functional AND gate.
It's a bunch of AND gates, a bunch of AND and OR gates. And you can imagine that in the simple-most model of what you imagine what a VHDL compiler will do to that thing, he has now a bunch of AND and OR gates, and it will clamp these AND and OR gates together to implement what you have written here on the screen. This is what happens here. And there's, as you notice, is dependent on the current state in A and B. They can all, from the perspective of this piece of code here, change at any given time. There's no clocking anywhere in that code here, which means it's just a bunch of AND and OR gates. And this combinational part is up here, this piece of logic. Takes an input, takes the previous state, produces a new state, and this can change at any frequency. So my input can change at gigahertz range. So does my output, but not your state machine. Your state machine is clocked here. Yeah?
With FPGAs, like what kind of latency would you be expecting if yours is purely combinatorial logic across the board?
Yeah, this is what your synthesis will actually tell you then in the end. You will actually calculate what is my latency which comes out of that one. So you can actually calculate that, you can design that carefully. And in those cases, you don't really care about those latencies because the clock signal will be will be most likely much, much slower than your combinational logic anyway. All right, that was fun with VHDL. Who are the logic fans here? You love logic? Are you at 1600 at the moment? You love logic? Good. You're prepared for the next step? That looks easy, right? Now this is the classical way to formulate concurrent, and in this case, time-oriented systems in a completely algebraic way. This is a process algebra, which is called time CSP. Who has been heard of or played with CSP in the past? So many? CSP means communicating sequential processes, and it is the classical logic programming abstraction from you have a number of sequential processes. How do you formulate the concurrency? By formulating the interaction between them, by formulating the messages between that. This one assumes nothing but synchronous message passing. It's the only form of interaction between these tasks, and you can logically derive everything else based on synchronous message passing. And this is the whole programming language. You can define your processes as any combination, of course now recursively, you can build it up recursively, of those expressions. And what that does, we will talk about next week. All right? Cool. I will also get next week away from the programming languages. And next week, I will also now start from bare physics. We'll start with sensor technology next week, because you need to have some idea how to measure things in the real world. What does that mean? How to do that, and how to connect this to your machine. Have a great weekend, guys.